Alright, so continuing on, chemical reactions and catalysts, part 2. We've talked about a catalyst, we've talked about what they do and how they do what they do. We've also talked about what enzymes are. So now we're going to take a closer look at how enzymes affect the speed of a chemical reaction. Before we do that, we have to talk about some key terms. The first term is called a substrate. The substrate is basically the reactants in the chemical reaction, what you start the reaction with. Followed by the active site. The active site is the spot on the enzyme where the substrates attach themselves. The shape of the active site is super specific. It's kind of like how puzzle pieces only fit with certain puzzle pieces, or how a lock and a key are specific to each other. So an active site is kind of like the lock, and the substrate is the key. And then you've got a time when the substrate and the enzymes are temporarily connected to each other. That's what we refer to as the enzyme-substrate complex. So when the enzyme and the substrate are connected to each other, this is where the old chemical bonds are broken and rearranged to form new chemical bonds. So here's a visual of how the enzyme works. Let's pretend that this is a chemical reaction involving the digestion of our food. So digestion normally takes anywhere between 24 to 48 hours. Now, if we didn't have enzymes in place, this process could take at least 2 weeks, maybe even a month, depending on the type of food that you eat. Can you imagine trying to digest something for like a month? Oh my gosh, that's too long. So luckily, we have enzymes to speed up this chemical reaction of digestion. Now, digestion is not just one chemical reaction, it is a series of chemical reactions that kind of happen one right after the other. So here, the substrate is the food in yellow. The substrate is what you start the chemical reaction with. So this food enters your body, goes down your esophagus, goes into your stomach, and in your stomach you have some enzymes. The enzyme is in red. So whatever food you put in finds its appropriate enzyme. Notice how the active site, this is the active site right here, okay, is specific to the food particle, or it's specific to the substrate. It will only fit in with that certain piece of food. So when they're temporarily connected in the enzyme-substrate complex, you see that it creates an image of like a whole complete piece, which is what you want. You want those old bonds to be broken and new bonds to be formed, so that the products in the end here, the third diagram, are completely different from what you started with. You started with a piece of food and you ended up with nutrients. And that means that the chemical reaction and the enzyme reaction was successful if you started with something and ended up with something completely different. There's a couple of key things to remember about any chemical reaction that involves an enzyme. Enzyme reactions are reversible. You can reverse the process, just like you can throw up your food. The enzymes are also reusable. Once they're done in a chemical reaction, they're simply just going to make a U-turn and go back to the next chemical reaction that they can be any help with. The third thing, enzymes never change in a reaction. The only thing that's changing are the reactants. The reactants are changing into the products. The enzymes are always going to stay the same. Now, oftentimes, enzymes work best in certain conditions. Some enzymes like the heat, other enzymes like the cold. So temperature is one of those outside factors that could definitely affect the way the enzyme works. For example, at very high amounts of heat, the enzyme denatures. Denatures means to change in shape. So if you look at this diagram, we have a certain enzyme in green. The perfect condition for this enzyme to work is at 40 degrees Celsius, which is right in the middle. Notice the active site, okay? If you lower the temperature just 10 degrees lower to 30 degrees Celsius, the active site is still the same, so the reaction can still happen. However, if you go 10 degrees higher to 50 degrees Celsius, look at the active site. It completely changes shape, so the reactant can't even fit in the active site anymore. So the reaction won't even take place. It has completely destroyed the enzyme. The temperature has, that is. Another outside factor that can affect the enzyme's conditions is the pH level. Again, pH measures the amount of hydrogen plus ions. So some enzymes work best at certain pH levels. So again, you've got our enzyme, it's in green on the diagram. It looks as if it works best at a pH level of 7 because it's right in the middle. Again, the pH scale goes from 0 to 14. So right in the middle would be 7. So our enzyme works best at a pH level of 7, which is neutral. It's not an acid, it's not a base. But if you go lower on the pH scale, so this side right here would be lower, okay? On the low end of the pH scale are the acids. So if you put the enzyme in an acid environment, the active site changes shape. So again, the substrate won't be able to fit in the active site, so the reaction can't take place. Same goes on the higher end of the pH scale. The higher end of the pH scale are typically bases. So if you put the enzyme in a basic environment, the active site will, again, change shape. The reactant cannot fit because it completely changed shape. So the chemical reaction itself won't be able to take place. Now, there are times where enzymes may need some helpers in order to speed up the chemical reaction. So we do have helpers. They're called cofactors and coenzymes. Both help the enzyme in doing its job, but they're not proteins. The enzyme itself is a protein. So in this case, a protein can't really help out a protein. It has to be something completely different. So coenzymes are organic, meaning our bodies naturally make them. We can add them in as needed, maybe through the food that we eat or maybe by taking any kind of multivitamin, because coenzymes are vitamins like vitamin E, vitamin C, vitamin B12. The cofactors, on the other hand, they're all inorganic. Our bodies don't make them, so we have to add them into our diet some way, somehow. So these would be minerals like zinc or calcium. That's why we have to make sure that we get enough like milk or eggs or cheese or anything with calcium, because our bodies can't make calcium. Now, enzymes also have enemies. The enzyme's worst enemy is called the inhibitor. And the inhibitor's main function is to stop or inhibit the enzyme's activity. So it basically stops the enzyme from speeding up a chemical reaction. There's 3 types of inhibitors: competitive, non-competitive, and feedback. The first type of inhibitor that we're going to talk about is called the competitive inhibitor. It blocks the normal substrate from attaching to the enzyme's active site. So it basically competes with the normal substrate. For example, penicillin. All right, so let's take a closer look at how the competitive inhibitor works. So there's 2 reactions pictured here, reaction A and reaction B. Reaction A is the normal enzyme reaction. So an enzyme has to speed up a chemical reaction. So the substrate is in green. The substrate attaches to the enzyme at the active site. It fits perfectly into the active site. They're temporarily connected so that the old chemical bonds can be broken and the new chemical bonds can be formed. And lastly, the products are released, and remember that the products are completely different from the reactants, what you started with. Notice the color and the shape change in the products, meaning a completely new product was formed. So that's how we would want an enzyme to work in any kind of chemical reaction in order to speed it up. Reaction B shows us the competitive inhibitor. The inhibitor is the turquoise looking structure. It competes with the normal substrate, so it blocks the enzyme's active site. When the active site is blocked, the normal substrate in green cannot bind to the enzyme, so the chemical reaction can't take place. Now, even though this may be the enzyme's worst enemy, it may not necessarily be our worst enemy. Inhibition for us, or competitive inhibition, I should say, could actually be a good thing, especially if we're sick. The example that was given to us for a competitive inhibitor is penicillin. Penicillin is kind of like an antibiotic that is still used today in order to help people get better if they're suffering from an illness. So let's say that the illness is the normal substrate, and it's binding to your immune system, that is the enzyme. So if the medicine is the inhibitor, so if penicillin is the inhibitor and it blocks your immune system, then you can't get sick because that normal substrate, which is your illness, can't get to your immune system and can't attack it, so you won't get sick. So again, competitive inhibitors are bad for the enzyme, but they're good for us. The second type of inhibitor is the non-competitive inhibitor. The non-competitive inhibitor attaches to another part of the enzyme, not the active site, but it causes the enzyme to shift a little bit, so the active site changes shape and then the chemical reaction can't happen because the substrate doesn't fit anymore. The examples for non-competitive inhibitors would be lead, mercury, or fluoride, similar to the fluoride treatment that you may get at your dentist.